So the upcoming talk is from University of Waterloo and is going to be presented by Annie Ray. And the title of the talk is Quasiprobabilistic Imaginary Time Evolution in Quantum Computers.
That's fine. Hello. Can people hear me?
If you want, I can raise the sensitivity.
Or could I put it somewhere closer?
Sure. If you want, I can put it on.
Okay, yeah, sure.
Oh,
Okay. Okay.
So 15 minutes, I'll give you a sign and 5 minutes.
Okay. Okay, great. Hello. I hope I'm audible to everybody, even in the back. Hi, everyone. My name is Annie. I'm a recent PhD graduate from the Institute for Quantum Computing. I've largely been working on error correction, but more recently, I've also been thinking about what it is that we can do with computers, quantum computers that we have available today. And that is the spirit of this talk. I will be speaking about quasi-probabilistic imaginary time evolution on quantum computers. It's a bit of a mouthful, but really we're just trying to do imaginary time evolution on quantum computers, and I'll tell you more about why. This is work that I did with my collaborators at IQC and at the Perimeter Institute. And yeah, we're in the process of writing up this paper. So yeah, I'd just like to acknowledge my collaborators. And just to give you a quick motivation for this work, and as we've heard from many other speakers during this conference, this work is largely in the space of quantum simulation, because we know that this is something that is a major potential application of quantum computers. And while quantum simulation is a very broad task and it entails a lot of different problems, in particular, this work is targeted towards estimating static properties of a quantum system. And that really means trying to estimate expectation values of some observable with respect to the state of the quantum system you're interested in. So for example, you might be interested in learning the ground state energy or the thermal state properties of a system. And so in this work, we're largely going to focus on the thermal state properties, and we're going to use a technique called imaginary time evolution to do this. So this is essentially a broad motivation, and our work is trying to figure out a way to do imaginary time evolution on quantum computers. So now that I've given you that motivation, let me quickly tell you how this talk is going to proceed. First, I'll tell you a bit about imaginary time evolution, and I'll then tell you how you would use that to estimate thermal properties of a quantum system. I'll then explain how we actually intend to do ITE on a quantum computer, and that entails doing using something called quasi-probability decompositions. I will then talk to you about how you can estimate expectation values using QPD. And finally, I'll show you some of our main results, which include both the costs of our algorithm and also a small demonstration that we were able to do of our protocol. And finally, I'll give you a summary of our results and tell you a bit about what needs to still be done. Okay. So as promised, and now I'm going to tell you a bit about imaginary time evolution. So we learned in quantum mechanics 1 that if you're given a closed quantum system described by some Hamiltonian H, then its state can be described by the Schrodinger equation. And using a simple transformation of that time variable t, also popularly known as the Wick rotation, where you take IT and call it your new time variable tau. This tau is actually now imaginary time because you've taken this product. And what that does is it transforms your real-time Schrodinger equation into this equation on the right, which is the imaginary time Schrodinger equation. And that also means that the propagator of the state of the quantum system in real time, which is given by the very famous real-time evolution operator over here, transforms into something that is known as the imaginary time evolution operator. So note that on the right, you don't have this I anymore, and tau is set to be some real number. So an important thing to note here is that this object is, yeah, as I said, it's called the imaginary time evolution operator. And this is non-unitary because it doesn't have that little I as a coefficient on the numerator, sorry, on the exponent. And this object also looks quite a lot like the thermal state of a quantum system. And if you replace the tau over here with some inverse temperature value beta, that's essentially what gives you the thermal state. And because this operator is non-unitary, you also have to normalize your quantum state by the partition function, which is defined as such. And so this is essentially the connection that we're trying to make between the imaginary time evolution operation and the thermal state. So this is why there's just one reason why you should care about imaginary time evolution is because it is somehow related to the thermal state. So now I'll tell you a bit more about how you can use imaginary time evolution to learn something about the thermal state. So the task is that you have to estimate some properties of the thermal state, and that basically means that if you have some expectation, so if you have some observable O, you wish to calculate the expectation values with respect to the thermal state rho beta, and this is the mathematical expression you essentially need to evaluate. And so one approach that is well known in literature is the process of preparing a thermal pure quantum state. So the thing to remember is that the thermal state is actually a mixed state, but this method, which is known in literature and is also referred to in this paper, is essentially that of preparing a pure quantum state. And this pure quantum state is given by an expression psi beta. And while it looks like a lot, the important things to remember are that you see this imaginary time evolution operator e to the minus beta h over 2 that makes an appearance. And you have a unitary applied to the state 0, onto which you apply your imaginary time evolution operator. So this pure quantum state psi beta can be prepared in this way. And U over here is picked to be randomly sampled from the n-cubic Clifford group. And by design, the thermal pure quantum state has the property that as you increase the size of your system n, you will find that calculating expectation values of observables with respect to the psi beta will give you closer and closer estimates of the expectation value for the thermal state of the quantum system. And so this is the property that we are going to use to essentially estimate properties of the thermal state. So just to reiterate, we're using the thermal pure quantum state psi beta and calculating expectation values of observables with respect to this state. And we're going to use that as an estimator for the actual thermal properties that you care about. So this is, as I said, what we're going to do. We're going to prepare this TPQ state by applying the ITE operator e to the minus beta h over 2 that you see here to some random Clifford state U, and calculate expectation values with respect to this state and use it as an estimator of thermal property of the system. So now the question is, how would you actually go about implementing a non-unitary operator like the ITE operation? And that's what we actually propose a method to do. So we're saying that we're going to take this non-unitary operation and be able to implement it on a quantum computer. So our algorithm that we came up with has 3 main ingredients. The first is that we're going to express this non-unitary operation that we care about implementing as a linear combination of the basis operations that you have available on a quantum device. So as we all know, it is usually assumed that these operations will be CP2P operations. And so we're going to express our non-unitary operation as a linear combination of those operations available to you on a device. Then we're going to use this linear combination, which I will refer to as QPD, and I'll say more about that in a bit. But we're going to use that QPD to randomly sample circuits from some probability distribution associated with that linear combination. And then finally, we measure the outcomes of these randomly sampled circuits, and we take the weighted sum of those measurement outcomes to essentially reconstruct the expectation value that you care about. So this is a high-level overview of the algorithm. And for those of you who have worked with in the field of error mitigation, you would know that this is actually very similar to an error mitigation strategy called probabilistic error cancellation. And just a quick sort of note about probabilistic error cancellation, in the context of error mitigation, it was used as a method to sort of undo the effects of noise by just sampling more from a noisy device and reconstructing the ideal values that you care about. So yeah, these are the three ingredients. And now I'm going to go through them one by one and talk more about what we do. So the first task is to express the operation that you wish to implement as a linear combination of basis operations. So let's say that I'll give you a note about what is the challenge in coming up with this linear combination. But let's say that we are able to write our non-unitary operation that you care about as a linear combination of some basis elements. So in our work on the LHS, we essentially just require that the operation that you wish to implement be hermeticity preserving, and it could be non-trace preserving. And one example is non-unitary operations like the ITE. And yeah, just a quick note that the curly T just means that it's the conjugation of the operator with the state that you want to apply it on. And on the right side, we have some completely positive operations that you might have access to. But the basis also generally will require some non-trace preserving elements. And these can typically be projective measurements on a quantum computer. So that's what the basis needs to be. And then we know that we can actually find a linear combination of such basis operations where the coefficients Qi are real, but they may be negative. And so the way that you would actually come up with such a linear combination is by trying to solve an optimization problem to minimize the distance between the stuff on the left and the stuff on the right. And that's how you would try to sort of come up with such a linear combination. And this linear combination is what we call a quasi-probability distribution. To be correct and exact, in literature, objects like this are called a quasi-probability distribution only if the sum of the coefficients Qi is equal to 1. In our case, this is not true because the thing on the left may be non-unitary and non-trace preserving. So we are basically just taking this word, quasi-probability distribution, to refer to this object. But strictly speaking, in a quasi-probability distribution, you need the sum of the coefficients to be 1, but we do not set that as a condition. So given this linear combination, you can write the absolute values of these coefficients Qi and call it a parameter gamma. And that allows you to define Pi, which is just the normalized values, the normalized absolute values of these coefficients. And if you look at it closely, you figure out that Pi is actually a true probability distribution because the sum of all the Pi's will be 1 and they're all positive numbers. And this also allows you to rewrite that linear combination in this way. So all we've done is that we've changed this Qi and written it as a product of its sign and its absolute value gamma times Pi. Another thing to note is that these linear combinations are not unique. The choice of your basis will essentially give you a different set of Qi's. And that means that even this parameter gamma can be different depending on what basis elements you choose. And this is an important thing to remember because we will speak a bit more about gamma in the future. So as an example, for a single qubit operation that you might want to implement on the left, so if curly T were a single qubit operation, we know from literature that this basis called the endo basis that was first discovered by Endo Suguru, which is a set of Clifford operations and some projective measurements comprising 16 elements. So these are a complete basis because if you think about it, you require 16 parameters to fully describe a single qubit process matrix. And so this is a simple example of what you might use as a basis in order to find such a linear combination. So this was a quick explanation of the first part where we're trying to find a linear combination of the operation that you wish to implement. The second part is to randomly sample circuits from the probability distribution that we created over here, which is the sum of absolute values normalized by, the absolute values normalized by the sum of all of them. And as I said before, it allows you to write this QPD in this fashion. And what that means is that you can, this expression basically suggests the way that you can probabilistically sample from this distribution Pi. And the way that it would look is this way. you essentially sample some n circuits from the probability distribution pi. And what that means is that for, let's say you pick a random circuit with some probability p1, for example, you will actually end up running on your quantum computer just this circuit, which comprises the first basis element, followed by the measurement of whatever observable it is that you're interested in estimating. And so this is essentially a very small schematic of our algorithm, which is that you sample from pi, and with different probabilities, you will essentially run different basis elements, and then you measure, and you take the weighted sum of the measurement outcomes to estimate this thing on the top, which would be the expectation value of observable A. And that can essentially, the numerator can essentially be rewritten in this form. And so when you take the weighted sum of the measurement outcomes of each of these individual circuits, what you're doing is you're calculating the expectation value of the outcomes with respect to these individual circuits, and you're weighing them by the factor gamma sine qi. Pi is just the probability with which you would sample these circuits. And so you end up being able to reconstruct from the weighted sum the objects in the numerator. But the other thing to remember is that because curly T is a non-unitary operation, or in general could be non-unitary, you also have to normalize the whole thing. And so you also need to make sure that you can calculate the denominator. And in particular, the thing to note is that you need to make sure that for the non-trace preserving elements you have in your basis, which as I said are typically projective measurements, you can calculate this trace BI for the non-TP elements by essentially calculating the post-selection rate of these particular circuits. So that's this last part of calculating the weighted sum. So the thing to remember is that our algorithm requires 2 gamma squared by epsilon squared times log something random circuits. And this is a gamma squared overhead as compared to if you had just had direct access to this curly T operation. And with these many samples, you can estimate the numerator up to some error epsilon with probability 1 minus delta, and similarly the denominator. And that allows you to estimate this ratio, which is what we actually care about because you need to normalize your expectation values with this much error. And note the dependence on this trace T rho. So this is essentially the main cost. And one interesting problem that we want to think more about is how you can actually reduce this value of gamma, which is the most important feature of our cost. And we find that if you modify your basis from the endo basis, which is essentially a full exhaustive basis decomposition, and allow for more entangling operations in your basis set, you can actually reduce the value of gamma to this orange plot, which is what you see for the Stuck-Huggy basis. But the lower bound is actually the diamond norm. And in this case, the decomposition would require just 2 basis elements, but they could be extremely entangled and are not necessarily very device friendly. And so really this whole area between the blue curve and the green curve is where you can optimize to sort of improve the value of gamma. So what we end up doing is that we actually try to estimate some thermal properties for the n-qubit 1D Heisenberg model by applying a trotterized version of the imaginary time evolution. And what that looks like is that you would essentially do a QPD for each of these local terms and sort of concatenate all the circuits and calculate the expectation values. So this was a very simple example. And what we essentially recovered over here was that there is an agreement between the expected behavior of these TPQ states, where the estimate towards thermal expectation values gets better and better. So on the left, we're plotting the error against the actual thermal state expectation value. And that this error decreases as you increase the number of qubits. So this is something that we were able to see in numerical experiments. Another thing that we saw was that if you were to just try to estimate energies after applying ITE on a noisy quantum computer, then you can actually take into account the noise in your device while you're doing this decomposition onto basis elements. And that basically allows us to have some noise resilience to the noise in our device and still be able to do this imaginary time evolution using QPDs. So some salient features of our algorithm, we can actually implement ITE on a quantum computer without using ancillary. And this is particularly in contrast to methods such as block encoding, where you might have to add some ancillary and also do some controlled operations between ancillary and the system. And this is quite expensive on NISQ devices, especially, which are which have significantly worse interaction operations rather than just single qubit operations. So this can be quite tricky. The second thing is, as I said before, we can actually make our algorithm noise resilient by taking into account the noise characterization info that you're given on a device. And you can take this info into your basis element and then do a linear decomposition. And finally, we believe that this is actually generalizable to general k-local Hamiltonians. So all you need to do is optimize a good basis for each of these local terms. And there the search space is essentially bounded. But once you have these like local QPDs that you can optimize for, you can apply this to do trotterized imaginary time evolution. It will be expensive in the number of samples you need to do, but if you pick a small enough value of gamma, it's actually possible to do. So yeah, just to quickly summarize, I presented a quasi-probabilistic algorithm for implementing imaginary time evolution on a quantum computer. And some of the things that we're thinking about more are how we would actually find a good basis to do this quasi-probability distribution, because there are two competing factors. One is to reduce the value of gamma, but also to have basis elements that are actually implementable on a device that is available to you. And the last thing we want to do is actually demonstrate this thermal state preparation on quantum computers for larger system sizes and see what we understand about thermal states of larger models. But yeah, that's my time. Thank you very much.
Any questions, Annie? Yep.